Alright, so our presentation is divided into 5 parts. As you can see, part 1 would be the objective as what we'll be learning in here today. Then a brief introduction about tunnel boring machine, its analysis, benefits and challenges, and some background about it. Then we'll go over the overview of the simulation as what will be the steps that we'll be taking in this demonstration today. And then for part 4 will be the simulation itself, where we'll be sharing as how the models are generated in the software called midas GTS. And towards the end we'll be concluding as what all we have learned, and if you have any questions and comments, then please share it with us after the conclusion part, or if you have questions in between, just use the chat window. Great. So the attendees of this session today will learn 3D numerical modeling of tunnel constructed using TBM, assessing tunnel boring machine forces and extract ground response accurately, then setting up of construction sequence quickly, and efficient result extraction for shield, segment and ground members. So let's move on to the introduction part here. So tunnel boring machine, basically these are the closed phase systems which advance through the ground by rotation of a cutting head, as you can see here, and this cutting head is propels forward by the reaction from the constructed lining behind it. And such tunneling has been traditionally limited to circular boreholes, because most of the tunnel boring machines are circular. But now with the different advancements in the field of technology and tunnel boring machines, you can have tunnels with all different cross-section shapes. So let's go over some historical background about the tunnel boring machine. So the tunnel boring machine was originally, tunnel boring was originally attempted over 150 years ago in England, Europe and North America. And the original attempts are generally considered failures, as the technology necessary to turn the scientific concepts into practical reality was lagging. So the engineers and scientists were ahead of their time. There's just one successful example of that era that was 1.5 kilometers long Shakespeare tunnel in Dover, and that tunnel was bored over 100 years ago. Then another major attempt to establish tunnel boring was made in the United States during early 1950s, and with some success in very soft rocks. And then the use of tunnel boring machines increased into the 1960s and 1970s with technological advancement that allowed successful tunnel boring in harder as well as less competent rock. So basically, with these advancements in the tunnel boring machine technology, now engineers are able to use the tunnel boring machines on not just soft grounds or soft rocks, but also hard rocks. And as the use of tunnel boring machine increased worldwide, they were also used in labor-rich and capital-poor countries because of inherent advantages, and because of overseas TBM contractors became very competitive with the local drill and blast excavation. So basically, there are some inherent advantages for tunnel boring machine, and I'm sure based on your experience you must be familiar with those advantages. So in the late 1960s and early 1970s, the question often asked was, can the tunnel be excavated by TBM? And now that same question has become, can you afford not to excavate with a tunnel boring machine? So you can see the change in the philosophy of tunnel boring machine and the engineers, how they approach different excavation problems. And this method has become increasingly popular for handling tunnel excavations in different types of terrains. So based on your experience, I would like to raise a poll and ask you to what extent you know about tunnel boring machines and their benefits. So I'm opening a poll right now. So what are the major benefits of using TBM? You can pick more than one. I'll read out the options. Is it the structural stability and safety at the face and the work area? And or is it the continuous non-cyclic operation that results in accelerated construction? Or it is consistent, less skilled and easily trained operations. So the labor force that is involved in this don't have to do heavy duty technical stuff. They can just take care of the rear end of the tunnel boring machine, which is a very straightforward job. Or one of the benefits is that it has safer and more pleasant working environment than in drill and blast. As you can know, drill and blast, you use dynamites there, and no one wants to be closer to dynamites. And it gives a better quality control. So far, 42% of the audience has voted, so I'm waiting for other engineers to give their poll. So we have almost 70%, 78% of the audience have voted. So I think we have some understanding about the benefits. So I'll close the poll as soon as you guys are done. Alright, so let me read out the poll results here. So 90% of the engineers believe that or know that the structural stability and safety at the face and work area is one of the prime benefits of tunnel boring machine. And about 80% of the engineers who voted here consider it leads to accelerated construction. And however, 23% engineers feel that it's not the main benefit of tunnel boring machine. That is you need consistent and less skilled labor. Where 68% believe that it has a safer and more pleasant working environment, and almost 61% of the audience who voted here feels that it provides better quality control for the tunnels. So thank you for your poll, and this gives us a better understanding about how you see different problems and how you simulate them, and what goes in your head when you are dealing with different types of projects. So as you rightly pointed out, the major benefit of using tunnel boring machine is the safety, the stability and the safety at the excavation phase, which is provided by the full face cutter head, as you can see here. Then the safety at the crown, which is provided by the cutter head shield. So if you have engineers in here, they are safeguarded against any inrush. So this is basically the work area of the tunnel boring machine, and there you have shields as well as jacks that are applied in the radial direction, so that any kind of fatal accidents can be avoided. So usually what happens is that when you hit a soft ground and it's a fault plane or something, that it mobilizes the entire rock strata around it, then if you're dealing with drill and blast, or if you're dealing with other conventional methodologies, then your workforce is highly at risk. So this shield alone avoids any kind of fatal accidents. Then behind work area safety is also important, and tunnel boring machine is able to handle that as well. So as and when you proceed construction and the tunnel boring machine propels forward, we immediately apply temporary supports on the excavated area, and these temporary supports could be the rock bolts, could be mesh shotcretes, or it could be steel ribs and lagging, and soon after that we are able to apply the permanent supports, which are usually like precast segments, as you can see here, or cast in place lining. So I understand that you all have a very good idea about the tunnel boring machine and its benefits. Now let's see what are the major challenges you face while simulating tunnel boring machine in numerical models. So I'll open this poll, and I will request you to give in your opinion as what are the major challenges you face while simulating tunnel boring machine during the construction staging. And you can pick more than one option because challenges could be many. It's not a question where it is correct or incorrect. So I'm seeing several engineers are giving in their vote. Let me read out the options or the candidates for this poll. So we have the first major challenge that has been pointed out, since we are talking about FEM modeling. Generating the 3D numerical model itself is a big challenge. Then the second is assessing the phase stability due to rock squeezing, which is a very main concern or a very big concern when you are dealing with tunnels through rock stratas. Then computing load computation as per ground response. So depending upon how much is the ground movement or the loss, how you can estimate that and convert that into load and apply it onto your excavation or on your tunnel boring machine itself. And then proposing or verifying the new developments in the machine system. So like I said in the very beginning, the technology is advancing and there are different developments coming in from mechanical engineers that aid the construction or excavation process. But being a geotechnical engineer who is responsible for designing these tunnels, he must be able to understand what are the new developments in the industry and how he can simulate it. So that is one of the challenges that has been proposed. Then last but not the least, and probably it has got the second or the third highest votes here, is extracting results in a usable or desirable format. Now geotechnical engineers have to communicate with structural engineers and erection engineers and fabricators. So you need to extract the results in different formats. For your presentations, for your contractors, you would need it in a PPT format, maybe an animation file, or you might need in spreadsheet format, in contours. So all different formats are available. So I can see more than 80% of the audience has already voted, so we can quickly go over the results of the poll. So 73% of the audience believe that generating 3D numerical model for TBM is the main challenge. Then 67% say that assessing the stability at the face due to rock squeezing. 87% say that load computation as per ground response is the main challenge. So, and 20% say verifying different machine system, and 45% say that extracting results in useful and desirable format. So you can clearly see that you guys have a common say regarding the challenges that you face. First and foremost is the generating the numerical model. The second most popular answer was load computation, and these are the things that we'll be focusing upon, and we'll be talking about why finite element analysis is needed and how we can simulate it. So let's see some challenges that why FEM is needed for tunnel boring machine analysis. So this is a screenshot from one of the reports, and here you can see, if you can read, it's pretty clear. In Venezuela, they are mining out the remains of tunnel boring machine that is trapped by squeezing of tunnel during a stoppage of the drive. So basically the rock squeezing was so much that it literally stopped the excavation process, and it even shattered or damage the tunnel boring machine, and they have to take out the remains. Point to be noted here is that the workers are still safe because the shield is still intact, but they cannot proceed with the excavation because their rotating head or the face is damaged because of excess of face pressure. So to simulate or understand how much face pressure would be occurring, you definitely need a finite element model. So this is a section that is cut through a 3D model, and you can see here there exists a plastic plastic zone around the excavation, and the soil or the rock strata tries to squeeze into any kind of opening that is there. Now, they are based on the constitutive material models and the soil properties. There are given values that you can use to predict or assume this squeezing in feature at work area or behind work area zone, but there's no way or standard computation formula available to assess what is the face pressure, because this is the first pressure that is exerted onto the face of the tunnel boring machine. It is absolutely critical. So you need finite element analysis to extract these forces that are occurring on the face pressure, and then apply the jack forces or the face pressure forces accordingly in your numerical model. So therefore, for ground squeezing, you needs accurate estimation of face pressure. Then let's see the next challenge. So this is another photograph from a project site where you can see there is a crane, a digger going in to excavate and clear the way, because the machine has hit a soft strata or something. So you can see immediate damage that has been caused. So in order to simulate these kinds of challenges and avoid any kind of surprises when you are doing the tunnel excavation, you must accurately model your soil strata. So based on your boring log data information, you should accurately model different layers of soil strata or rock strata and model the interfaces as well as their constitutive material property, so that while you are doing the construction, you are able to simulate this is how the deformation would occur if this is in excess to what you have designed your lining for or your tunnel shield for. Then you should definitely go back and reevaluate those designs. So even before the construction goes out in the field, you should simulate the construction sequence and see if we have removed these much stresses from the system, what the deformation would be. So basically, soft pockets and faults need appropriate constitutive material models and interface controls. And talking about interface controls, today I'll not be going into this aspect in that detail. We'll be having a follow-up session in 2 weeks from now, and then we'll be taking up this particular issue which occurs with fault planes and slipping of fault planes, and if you are tied up with a project that there is no option but the tunnel is going through your jointed rock mass, how to simulate it in a finite element model, not in a discontinuous model. So that will be our topic in the upcoming sessions. And one other challenge that engineers face is simulating the advancements in the tunnel boring machines. So this is and one of, I should not call the latest because it's ever evolving, but this is a new, relatively new development where they've applied parallel blades on the shield, so that when you are doing the tunnel excavation, it locks the shield. If you are not digging further, like in the longitudinal direction, it will lock the shield in that position and the stresses around it. So this is increases the safety, and once you start drilling, it will aid in the excavation itself because it's also rotating and clearing out the additional area. So in order to simulate these kinds of advancements in the field, you definitely need a tool where you can accurately see what's going on and to what extent the stresses are propagating or the displacements are occurring, and if needed, if your excavation is halted in between and you are applying some special types of hydraulic jacks to stabilize the excavation, then you can very well apply those kinds of temporary supports also if needed. So very important for numerical modelers is that in order to simulate these new developments, you definitely need a good 3D modeling tool to replicate the effects of the new developments in tunnel boring machines. So let's now move on to the overview of the simulations. So basically, this is the sample problem I will be going over today. It's a shield TBM problem, and it is a relatively simple soil setup because I wanted to focus on how to simulate excavation sequence. So this is a ground, and we have the internal excavation layer, that is the diameter of the tunnel actual opening. Then we have another set of excavation which is called the external excavation that will be later on replaced by the segment. These can be the precast segments of concrete, and there is tunnel lining also. So before the segments are installed, there is lining, and then this lining is replaced, and then we have the segments installed, and between the segments and the actual ground there will be grouting. So this linings would be then replaced with the grouting material. So if you see the cross section, we have the excavation soil, which is this, then we have this shield TBM right around it, and then we'll have the segments that will come in, which is this pink zone, and we'll replace this shield of the TBM with the grout member later on as and when the excavation proceeds, and we'll have the soil around it. So let's see what are the steps or the main steps that I will be taking up today. So first step, we'll be defining the attributes for ground, segment, shield, and grout. Then step 2 would be geometry generation using the solid elements for ground and tunnel segments. Then mesh generation using auto meshing features, and from these 3D auto mesh we'll be extracting the lining members from these solids. So we'll basically go from 3D to 2D. Then for boundary condition, we'll apply just the ground supports, and then we'll define the loads, and this will be the second most popular challenge that you propose or voted for, how to define these loads and assess these loads. So I'll be talking about surface, phase pressure, contraction over the body of the shield TBM, gap consideration between shield TBM and the segment diameter, and the jack forces, because ultimately you are pushing the tunnel boring machine forward. Then we'll be setting up the construction sequence, and I'll use some sort of construction stage analysis control to define how the construction has to be proceeded. Then we'll be running the analysis. Actually, I'm running it right now in the background so that I can share the results directly with you, and then we'll be extracting the results. So let's go over the simulations directly. So first step, that is the attribute definition, and as you can see, we call attribute is a sum of the material ID and the property ID. So material ID is let me explain you with an example. So let's say we are talking about shield. So shield is an attribute which has been applied to plane members, that is 2D members, and the material ID or the material will be steel, but this plate will have some thickness, or the shield will have some thickness, so there is a property also associated. So you can define the shield thickness also, and then to the measure that this will be applied will be called shield. So basically attribute is a combination of what type of element this will be assigned to, what material property or the constitutive material property it will have, and what type of property that will be assigned. So basically the thickness. So whenever you are using rock bolts, this property can have the thickness of the rock bolts or soil nails. If you're using sheet pile, then you can give the thickness of the sheet pile. So different type of properties can be assigned, usually for the structural members. So you can see the properties that will be assigned for the shield and grout. We are going with the 0.06 of the meters. I am sticking to the SI units here because we have major audience from US and Canada, and I just wanted to stick to the standard unit system here. So this is the material ID. You can see ground material will be of solid type because we'll be assigning it to the solids. We'll have more coulomb as the constitutive material model, and the properties are shown here. Similarly, for the segments, we'll have elastic. This means it's concrete. For steel, we'll use elastic, and for grout, we'll use elastic. So basically, grout and segments are steel, are concrete, and steel is obviously steel. So you can see the properties accordingly. The strength of grout is obviously different from the concrete of segments, so you can see and vary the properties here. So what I'll do is go into the software itself and show you how this has been defined. So let me open the member of the folder here real quick. So I've created some step-by-step model files so that we can quickly walk through it. So I'll be starting with the very first start file. So here, this is how midas GTS looks like. This is the grid. You can turn it off. And on the left hand side, you will see this is the model tab. And in the model tab, you can see properties. And the properties, you can see attributes. Under attributes, you can see the attributes has been assigned to plane members and solids. So let's start with the material property first. So we'll go to material here. You can see the material for structural members, which is steel and grout, and for the ground members, which is ground itself, and segment, which is actually solid. So if I just right click and go to edit, you can see its property right here. So when we start, we first start with the defining all the material properties. So we throw in the parameters, choose the constitutive material model. Now depending upon to what extent of information you have regarding the soil strata, you can pick the most appropriate constitutive material model from here. If you don't have, if you don't find the one that you are looking for, or if you have your own defined material property, you can just switch to user supplied material property, and you can create your own constitutive material model. So once the material properties have been defined, then we define the structural properties. So you can go to model here, and the property, you can find attribute, material, and property. You go to property here, then you click add, and then you can define you would like to use if it is 1D member, or if you want to use for 2D member, and what thickness you would like to apply. So we have applied shield and grout here, and once you have defined the material and property, then you go to attribute, and here you can start by, let's say, for solid, and you can select the material property, let's say ground, and if you want to modify it, then you can go ahead and modify, and then just hit apply. So in this manner, we can define the ground, so similarly segment, shield, and grout. So if I double click on shield, you can see we have the material property as well as the element property. So right here, so steel and shield together. And if you have already defined these attributes in your previous model file, or you're creating a copy of the same model file, then you can also import the material properties from your previous projects. So it doesn't mean that you have to, if you're dealing with same soil strata or same set of segment and lining members, then you can just define it once and then import it anytime you want. So in this way we define the material attribute, and you must be noticing what the square and the two circles are. I'll come to this in a bit. So once the properties are defined, then we start by defining the geometry. So the first and foremost step is that bring in your DXF drawings. If you have DXF drawings, then use it. If you have it in 2D or 3D, just directly import it into the software. If you don't have these DXF drawings, then you can create these cross-section very easily in the same software. So once you have got the basic outline as where your tunnel is located, the inner circle and the outer circle, and your far field boundaries, like to what extent you would like to have your soil strata around it for investigation, so then you can start by creating this 3D model from a 2D. So what we'll do is, just using this 2D geometry line, we'll extrude it into a 3D solid. And once we have generated a solid from it, then since we'll be doing construction stage analysis, we'll divide this tunnel into number of segments, and for this we'll create a plane and divide the solid. So let me go through this. Go through these steps. So this is the 2D profile. Like I said, if you don't have this information, you can easily use these create rectangles, create arcs, create circle commands, and easily generate your drawings here. But if you do have the DXF drawings, then you can directly import them from 2D, 3D, or different file formats. Having said this, let's start generating the model from 2D to 3D. So I'll go, since I want to create a solid, I'll just go to solid and I'll select extrude button here, and then I want to select this wireframe. So I'll change the filter from face to wire, and then just select all the wires here. So you can see 3 profiles selected, and I want it to be extruded along this axis, so you can see which is global Y. So I'll just say select extrusion direction and directly click on the axis, so you can see the axis selected, and then I'll give the length. So I'll go by unit length, and I'll just directly create the entire length, which is 20, and I'll give it some name. Let's say extrude for now, and I'll say preview. So in preview it will show you that 3 solids will be extruded: the inner circle, the outer circle, and the ground. So I'll say OK here, and if you see in the geometry, you'll see 3 solids are created, and all the 3 are named same because I didn't change the name. So what I'll do is just click on the solid. I can see which solid is being highlighted, and this is definitely ground. So I'll just hit F2 from the keyboard and change the name to ground. Hit enter. Then I will click on the second one, and I'll see it is the inner circle that has been selected. I can just zoom in so that you can see it more clearly. So I'll just click here. The inner one is selected. I'll just change the name to inner, and this will definitely be outer. So I'll just hit F2 and change the name. So once these 3 names are clear, now I can go ahead and start doing the modeling. So if I click on ground, I'll hide it. So you can see this is the complete solid. If I check off inner, and then if I you can see, let me just turn off the curves here. So you can see this is just one solid. So outer is actually a solid, whereas I want the this solid to be in a pipe format, so it should have a cavity for the excavation of the inner circles. And similarly, if I check everything off and I check on ground, you can see it is a solid again. There is no opening in there. So basically all these solids, although they seem to be on the same profile, but they are actually just overlapping. So what I'll do is quickly embed these solids to create cavities. So I'll start with ground. So I'll go and use a feature called embed, and then I'll select the master object here, and then I'll select the tool object. So tool object, either I can directly click here and select, or I can just click on the name of the solid here. So I'll say outer, and I'll check on delete the original shapes, and then use preview button. So it will show you a solid with dotted lines, and I'll say apply. So now if I check off everything here, you will see the ground is now having a hollow cavity in it. Now I want to repeat this to my inner and outer circles. So I'll say master object, let's say the outer one, which is the outer, and the inner one I can just say inner from here, and I'll say preview, and then I'll say OK. So now if I turn off the inner, you can see it is a hollow outer circle. So it is, you can see it like inner, then outer, and then ground. So in this way, now all these members are sharing surfaces, and they know that we are embedded into each other. And now what I'll do is create an arbitrary plane and divide this tunnel into a number of lines. So I'll just go to curve and select create rectangle, and I will create a face. And all I need to do is just click here, drag my mouse, and create an arbitrary plane here like this. And I want to make copies of this plane, so I'll just say translate. I'll select this and say I want to go it in this direction, so I'll just click on the axis, and I'll make uniform copies, unit distance, let's say 19 times, preview. So the program will create copies of this, and then I'll say OK. It's done. And now I'll use these planes to divide the tunnel into segments. So I'll just use solid, and I'll say divide by solid by surface, and I'll select the outer circle and press down the control button and select the inner circle. So two solids are selected, and then I'll select the surfaces. So I'll click here, you can see the 20 surfaces that are there. So I can just click on the first one and then press the shift button and select all. So all these surfaces are selected, and then I'll say divide the touching faces of the neighbor, and that will be my ground. So I'll just click here and select ground, and then I'll say preview. So now the program is actually, you can see how the dividing is being done. So you can see the tunnel section will be divided, but not my ground like into pieces, but the tunnel section will be divided and the ground will be divided at that location only. So I'll hit the OK button here, and you can see the tunnel divided. So you can see outer D1, D2, D3, and so on and so forth. So we have done this much. Now let's move on to the step 3 here. So step 3 is generate meshes. So first we'll define the size of the seeds to control the mesh size. Once we have done that, we'll use a feature called auto meshing for solids to generate the solid mesh. And then we'll extract the lining members from the outer periphery of our solid. And since this lining will be outside the segment, so we'll be extracting this from the outer circle, basically the outer circle that we have in this tunnel. So let's see how this is done. So just to be on the same page, I'll just open the next file, which is mesh start. So it's the same wall here, and you can see under the geometry we have all the solids D1, D2, D3, D4 divided, and now we'll start defining their meshes. So What we'll do is we'll directly go to mesh and auto mesh solid, and then I'll select the solids that I would like to start with. Now as a thumb rule, you should always go from interior to exterior, so I'll start with inner circle, and I'll press the shift button and select all the inner circles. So you can see 20 members selected because we divided into 20 segments, and the element size here I'm giving is 1, and the property would be ground because initially it's ground material, and I will give its name as inner. Let's say, just to distinguish them, inner circle, and I'll say preview. So you can see some dots created. This means these are the seed size, and then I'll say apply. So this is how the meshing is done. You can see the mesh generated the inner circle, and if you come here and you'll see mesh sets are created for inner circle. Now similarly, I'll repeat it for the exterior or the outer circle. So I'll click here and press shift and select all the outer circles and just change the name from inner to outer. And I'll use the preview button. So you can see this time the meshes are created, seed size are created on the outer circle, and I'll say apply. So you can see how quickly the meshing has been done. So the exterior or the outer circle meshes are also done. You can see 41 mesh sets now. And then last but not the least, and probably the most important one, is our ground. So I'll say unit size is 4, and I'll change the name as ground, and I'll select the solid that represents the ground. Right here, and then I'll say preview. You can see how the mesh sizes are defined, and then I'll say OK, and the meshing is done. So we're done with the meshing. You can see for 41 solids we have 42 meshes. This is the default mesh set, and you can probably see them individually if you want. You can see them, they are numbered accordingly. So if I turn off the ground here, you can see the solids inside, and let me just turn off all the geometry curves, so now you can see it more clearly. So you can see the inner circles, and then you can see the outer circles, so and so forth. Alright, so now we will be extracting the lining from the outer circles. So what I'll do is just hide all the meshes for now. So I'll just check this out. So all meshes are hidden, and from solids I'll extract this 2D member. And the beauty of this tool is that it will understand that this solid has already been meshed. So the new mesh that it will be creating, it will be automatically meshed and matched with the nodes. So I'll select all the outer circle members, I press the shift button, right click and say show only, so that you can see only the outer circles, and I'll go to model, element, and extract element, and here I'll select based on the command is, let's say, faces, and let me go to the side view here so that you can see it more clearly, and I'll just click and drag my mouse to select all the faces. And very important step is to skip the duplicate surfaces, because between every segment or every outer circle, between every two circles, there will be a face. So the program will otherwise extract the members for that face also, which is not needed for lining because it is just the outer periphery. So I'll change the material property name to our attribute name to shield, and the name as shield, and I want this shield to be named as per the owner object. So this means that it will, once I hit OK button, it will create the mesh and its names also. So here you can see, let me just hide all the solids, So now the program has created the lining, but you can see the lining has been created and it has been applied on this member also. So what we'll do is we'll delete the members that we don't need. I'll go to the left view again and hit F12 from the keyboard, that is the delete command, or you can also find it in the model and the steps here, and I'll just select this face, I'll select this face and hit apply. So now if I go to the cross-section view, you can see there are two circles. This is the outer periphery, this is the inner periphery, and I don't need inner periphery. So what I'll do is use select by polygon feature and quickly create a polygon to enclose all the members and select them. Now this can be of any shape, any number of sides, and you can easily create and select all the members that are in there and then hit OK to delete them. So now what are we left with is just the lining, and we are calling it shield. So you can see under mesh sets, if I expand it, so it is inner circle, then outer circle, ground, and then the newly created shield members. Now one more thing that we should do, if let's say if I want to see where is shield number 1, so or shield, I click here, it is somewhere in between. Shield 1 is somewhere here. So basically they are not numbered, and in order to simulate a construction sequence, I want them to be aligned in a particular manner. So for this, what I'll do is I'll go to the mesh and go to mesh set and say rename. This will make my life very easy because I can easily rename all the mesh sets in a given sequence and then control it during construction staging. So what I'll do is select all the mesh sets here from shield to, let's say, shield 19. So 20 mesh sets are selected, and I want to align them as per the coordinates, and my first preference should be Y. So because I want to go along the Y axis, so this should be 1, 2, 3, and so on and so forth. So 1 should be here and 20th should be there. So I'll give the first order as Y, and I'll give its name as shield, and then I'll say apply. Once I do that, you can see they are aligned. So this is shield number 4, this will be shield number 16. So they are not ordered here, but in sequence, if you see, like shield number 1 is right here. Then if I say shield number 2, should be somewhere here. Shield 2, then shield 3, and so on and so forth. And you can also arrange them with the names also. So you can use sort them or reset them, and all those options are available. So you can sort them by creation or by name. So I'll say by name. So here now you will see them, all of them are aligned. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 till 20. Now we'll repeat the same step for getting my outer and the inner circles aligned. So I'll just say inner circle from here to 20. Like this, and same preference order, just change the name to inner circle and say apply. So now this has also been renamed, and then I'll similarly repeat it for the outer circles. And you'll realize that how simple this will make my defining of construction stages. Then okay, so all these has been renamed. So now what I'll do, and since I have defined all these methods of like the inner circle and the outer circle with same material properties, but during construction their material property will change. They will change from ground, which is right now ground, to the segment properties, which is concrete, and the lining, which is shield right now, will change from shield to grouting. So what I'll do is, there's a command in the software that allows you to modify or change the element attribute for the construction stages. It's called change element attribute for CS, and here I can select the mesh sets. So the mesh sets I'll select for the outer circle. So all the outer circles during construction stage, when I activate them, I'll have a command which will allow me to switch their property from ground to segment, and I'll say apply. And similarly, all my shield members, so from here to here, would be transformed from shield property to ground, and then I'll say OK. So this is a type of boundary condition that we have defined, and if you go to the analysis and if you go under boundary, you will see all these conditions defined. So when you are doing the construction stages, all you need to do is, when you want to switch the property of this ground material for this outer circle from ground to segment, you can just activate this boundary condition at that time. Then once this has been generated, what we will be doing is we'll go ahead and apply the boundary checks. So before this, let me just quickly show it to you. So when defining the boundary, we'll first check whether our mesh that is being generated is correct or not. And for this, we have a feature called free faces. Once we do that, we can see all the outer periphery to have orange color. But if I see anything orange inside this mesh, like a continuous surface inside this mesh, this clearly goes to show that this is an independent surface which is not connected to the neighboring solids, and therefore your meshing is not correct, and you'll get faulty results. So first we'll verify this, and then we'll assign the auto-generated ground supports. So for this, let me open the next model file. So I'm not saving any changes to my initial model files so that I can use this over and over again, or I can share it with all my users of the software so that they can also practice after this training session. So if I go back to the model here, you can see the meshes that have been generated, and they have been ordered also. So inner 01 to 20, then outer 01 to 20, and shield, let me just sort them as per name. So you can see them ordered now. And under analysis, you can see the boundaries also created. So now we'll go ahead and apply the first we'll apply the check. So for this, I'll undisplay all the mesh sets and directly go to mesh, and here we'll say check mesh, and I'll check on free faces. So if there are any free faces, it'll show up in orange color, and I'll say apply. So there are no free faces inside the mesh set. You can see only on the outer surface you have an outline, but if it was a free face inside, you would have been able to see some solid orange mesh set inside it. So this means our meshing is accurate. Now I'll turn on all the mesh sets and go to model and go to boundary and define ground supports. And the program is intelligent enough to understand the entire mesh set and find out which is the outermost surface or the edge and apply the supports to that. So I'll just enter the name as ground support for the mesh set, and this just hit the OK button. Once I did that, you will see under boundary a new boundary ground support created. If you want to see it, you can just check this on, and you can see the program has applied the boundary support all around the periphery of the of this model. So this is how simple it is in GTS to generate the boundaries. And in the same model, let me just quickly define the self weight also. So I'll go to model and I'll go to load, and under load set I'll define the name as SW for self-weight and add, and I can define, I'll be applying horizontal pressure for the face. I'll apply jack force, so I can create any number of load sets here. So let's say I want to have HP, and I want to horizontal pressure, and I want to add for up to 9 segments, so I can just say HP2, HP3, so and so forth. So in this way you can define the load sets name easily, and I'll go to model, load, and then I'll define as a load for self-weight, which is SW here, and it will be applied in the gravitational direction, which is Z, and downwards, so therefore -1. So what the program will do, it will compute all the material properties and the attributes, and apply the area of the member times the density, and then multiply by -1 and apply it as the self-weight onto the structure. Now sometimes engineers don't want to consider the self-weight effects, so you can still run the software and ignore your self-weight, so that you don't get any effects due to self-weight of the structure. But it is useful to consider the self-weight for initial stresses, so therefore we have defined the self-weight here. Alright, so once we have defined the boundary conditions, let's move to the next step, which is the ground response to the tunnel construction. So since majority of the engineers have already attended the previous session, you will have seen this slide before, and like I promised last time, we will be sharing it in more detail in this session. So here you can see the major ground losses that occur when you are doing tunnel boring machine excavation, and first and foremost is the face loss or the face pressure that occurs on the face of the tunnel bore itself, then or the cutter head, and then you have the shield loss that is occurring due to the inrush of the soil or the rock strata onto the shield members. And once the machine moves forward, you have the grouting member and the permanent lining, so the deformation of the soil that continues to occur after that also is to be accounted for. So there are different types of losses that you have to consider, and to greater extent there are formulations and computations already provided that you have to use to generate or compute these forces. So I'll go over them one by one. So just a brief recap, we'll be computing first the face pressure, second the contraction force on the shield members, then third the tail or the gap closure, which is the deformation that will occur, or the forces that would be equivalent to cause that deformation for the actual tunnel segment and the grouting member, so this gap. And then there will be a computation of the jack force, which will be in the longitudinal direction. So the face pressure. So for estimating the face pressure, if you remember, this is one of the main challenges when you're dealing with tunnel boring machine, and this has led to several complications in the field. So in order to assess the face pressure accurately, what you have to do is first create a 3D model which is static. So you are not simulating any construction sequence in there. You just create a model with and apply the supports here, and under its own surface see how the structure or the soil strata is deforming and exerting pressure or trying to come into that opening. So you will see how the deformation or the stresses are occurring, and then you can see, you can take the summation of all those reactions that are occurring at the face of your tunnel excavation. Once you take the summation, you will get to know what is the face pressure coming from the surface of the structure or surface of the soil strata. Now in order to get the actual face pressure, you have to take out some effects due to other, the force pressure that would be occurring due to other sources, whereas which basically comes from the theoretical computation point of view, that is based on the height and the K0 value, and then see the lateral pressures. So this calculated or computed from the 3D finite element model, you have to correct it for the theoretical loss and then come up with the final total phase pressure. So once we have computed the total phase pressure, this is how we'll be applying it. Since we'll be applying the phase pressure at different intervals because our construction will proceed in certain increments, so we'll select only those members of the inner circle and apply the pressure on their faces. Now we'll use a temporary a new load set called temporary, so that we can just apply all these loads and identify these loads with just one name. Once we have applied these loads under one name, that is temporary, we'll copy this table from midas GTS into a spreadsheet. And when we do that, we'll be able to easily change the load set name from temporary to whatever we want. And we want it to be HP1, HP2, HP3, HP4. So through this way, we can quickly change the load set's name and apply them, and use this nomenclature to our advantage when we are doing construction stage analysis. So this is a tip to all our midas GTS users in the session today, that instead of applying forces one by one on each phase, you can always apply them as one shot and then quickly change their name from spreadsheets. Other alternate is you select HP1 in the load set name, select one phase, apply it, then change the name to HP2, and so on and so forth, and proceed. So that's a time consuming process, and I just wanted to explain it to you to make it simple. Alright, so let me go into the model itself, and this time let me open the next model file where I've already defined the load set names, just to save some time. So we'll go to this model file called load start and drag it and drop it over the screen here. And it'll open the load start file. So this is the file where we have already defined the load sets in the same command area that I told you before. So we have defined HP1, HP2 to HP9 and so on and so forth. So what I'll do is just quickly start defining the loads. So we'll select the inner circles or the inner solids. And another important thing to be noted here is that we have already meshed these solids and we are applying these loads onto these solids, because when you are running the analysis, the program automatically converts the loads that are applied to the geometry, we call solids as geometry, to the mesh sets automatically. So again, this will make your modeling process much more easier, which other software are not able to do. So here we'll be it is much more easier to select these solids and apply the loads rather than selecting individual mesh object and then applying the pressure load. If you intend to do, if it's a small model or if it's just a localized need, then you can do it that way also. But again, this is just another tip for our GTS users. So here I'll select the inner solids. So let me just undisplay all the mesh sets so they're not confusing. So I'll click on inner solid, and I want to select, since I'll be excavating in certain increments, so I'll select 3rd, 5th, 7th, 9th, 11th. These are based on the excavation the length of the excavation that I want to go, the increments 17 and 19. So say I've activated these members, and then I'll go to model, load, and select pressure loads, and here I'll enter the name as temporary, and I'll I'll just go to the left view here so you can see them more clearly. I'll apply it to the element face, and I'll just select the element face like this. So I'm just selecting the face, so you can see the face pressure element, free element face, sorry. So basically, while selecting the face, I have to rotate this like this and then select the faces. So what I'm doing right now is just going by surface, so I can just make the selection of surfaces like this. So in this manner you can select 9 surfaces, and then the direction. Now again, the direction could be normal, and most of the cases we apply pressure in the normal direction, but whenever you are doing tunnel construction, everything should be as per the global coordinate system, or should be in line with global coordinate system. So what we'll do is, after selecting these faces, we'll just say select the direction as per this axis. So this is the direction of excavation. I'll select this as the direction, and I'll enter the value that we just computed, so which is 21.56 units, and then I'll say display, so you can see the pressure applied onto the solid faces, and then I'll say OK. So in this manner the forces are applied. You see the forces being applied here, and what we'll do from now on is convert these forces into change their names basically. So I'll go to analysis, and I'll go to load here, and you can see there's a plus sign against temporary, so this is the only force that we have applied, and I'll just right click and say tables. So you can see the table generated very easily, and all I need to do is just copy the entire table, or I can just copy the values, hit Ctrl C from the keyboard, open Microsoft Excel, just hit Ctrl V to paste it, and here I'll say HP1 and change all the names here from 1 to 9, copy it, come back here, click on the very first field and hit Ctrl V to paste it. There you go. And now I don't need these temporary, so I'll just select all these and hit delete. So in this manner you can see the plus is no more in front of temporary, but it is now in front of HP1, HP2, HP3, HP4, and so on and so forth. So in this manner we can apply these loads onto the solids, and there exists an option from where you can convert this load from the solid geometry to finite element. So it's called transfer to FE, and the program will automatically change this loading into finite element loading, as you can see here. So it is based on the mesh size, the program has automatically distributed this load onto the mesh set. This is a very good feature and saves a lot of time, and it is not important, I mean it is not at all mandatory for you to every time switch or transfer these loads into finite element loads. The program automatically does that whenever you're doing the analysis. Alright, in the same manner we'll apply the jack force onto the structure, and so on and so forth, and change their names. So I'm not doing those repetitive steps, but what I'll be talking about is how to compute these contraction forces over shield and the gap between the shield and the segment. So first let's talk about the contraction over the body of the shield TBM, and as you know, contraction pressure is given by the simple straightforward formula, where this is delta R is the change in the radius or the diameter. You can make it twice, and you have to compute the strain. So basically this delta R is something that is based on your 2% volume loss, or you can say based on the core softening, or based on your gap method. So no, irrespective of what method you have adopted or what core you are following, or what practices or what has been recommended from your contractor or the owner's guidelines, you can use this value and generate the pressure force. So in the same manner, here we have for the contraction over the body of the shield TBM, we have used 0.02 units, and this is the loading that we get, and this load will be applied onto the shield or the lining members. Then we'll apply the gap loading, where the delta R would be 0.11, which is greater, and that is what is expected also. And a tip for all the GTS users or any tunnel boring machine engineer, or I mean basically for all the tunneling guys here, always try to use a value lower than what is being given in the codes. And it's just a suggestion, don't use it as a thumb rule, because what happens is, let's say the code said is 2%. So I would start by 1.1 or 1.2%, because what will happen once the tunnel is completed, there will still be deformations going on, or after setting up these segments, there will be deformation in the segments itself. There will be creep and shrinkage in the concrete itself. So it will shrink, and there will be further losses, and there is external pressure already. So from 1.2, 1.5, then overall deformation would be 2%. So majority of the time where engineers go wrong or make this, I should not say a blunder mistake, but this type of things is very human and can come in. So if you are taking care of this, it's brilliant. If you are not, then it's just a suggestion, because you have seen some of our the model files in the past, and we have pointed this out to several of our users also. So just to share the word here. Then computation of jack force is also pretty interesting and straightforward. It is basically skin resistant forces plus the face pressure forces, and all the dimensions of the tunnel boring machines that are needed are provided by the manufacturer. So you basically know the diameter, you know the weight, you know the coefficient of friction between the pipe and the solid, then soil cohesion, the length of the shield. So all these parameters are given to you, and then obviously you'll have the boring log data, so you'll have the properties of the soil and the segment data, because it's a segment area, because you know they are precast members. So based on these parameters, you'll throw in the formula where you have to find out the skin resistant forces. So basically it is the skin friction force between the soil and the shield TBM plus or minus skin friction forces due to the difference of unit weight of the ground minus unit weight of the TBM. Now the reason we have used plus minus, because sometimes the unit weight of the ground is higher than the unit weight of the shield TBM, or vice versa, depending upon what depth you're working on. So you can throw it in the formula, which is actually just the surface area times the coefficients, to generate and obtain the skin friction forces. Once you have obtained this skin friction forces, you should add the face pressure that you first computed times the tunnel area that is excavated to get the jack forces. Now this is something that engineers often miss out, and this number 21.56 units doesn't seem to be big or comparable to 22.71, but once you multiply it to the tunnel excavation area, the overall value is increased. So sometimes engineers, while making assumptions, they miss out on certain minute details. So again, it's a tip. Don't, if possible, try to avoid these mistakes. And then the jack pressure will actually be the total jack force that we have obtained divided by the segment area itself. So that it's a pressure, and you can apply it on the segment members. So once we have obtained this, then we can apply it in the same manner like we applied the horizontal forces or the horizontal pressure. Now after this step, we will move on to construction sequence, And for this, let me open the model file for starting the construction stage analysis. Alright, so now if you remember from the last presentation or the last session, we talked about having construction sequence laid down in a spreadsheet format. So this is the reason why we were doing all the renaming and naming them in certain order. We have to control as when and where these segments are to be activated, when and where the lining members are to be activated. So and whenever we deactivate something, that means we are excavating it. So first we activate the entire soil strata, and with the soil strata we also activate all the inner and the outer circles, because initially they are all made from ground material. Then we deactivate the inner circle and the outer circle 1 and 2, because this is the 1 and 2 combined is the length of our increment of excavation, or excavation increment, which is actually 2 units, because each length of each circle is a unit. So we'll take out 2 inner circles and 2 outer circles, and we'll add the shield for the first 2 units. So we'll activate shield 1 and 2. When we are doing this, since the tunnel machine is already starting is inside the ground, so we'll apply the horizontal pressure, which is actually the face pressure, onto the inner circle, and S1, which is actually the contraction pressure that is coming onto the shield members, which is on the outer circle. So we'll activate the shield pressure, or I should say the contraction pressure. Then we'll deactivate next 2 segments, 3-4 for inner, 3-4 for outer, and activate the shield for 3-4. And then since the machine has moved forward, we'll apply HP2. And once the members are deactivated, automatically the loads that are applied to it are also deactivated. So you don't have to think that I applied pressure certain time and now I have to deactivate it even if my mesh set is not there. So it moves forward, HP2, S2, and so on and so forth. So you can see it's a very repetitive process. So if you can prepare this kind of construction schedule and match your names accordingly, it will make your life much more easier. So, and then after step 5, when we have already excavated for 4 increments or 8 units, then we'll start constructing these segments. So we'll activate the outer circle members, which were deactivated in the first stage, but when we are activating them here, we are also adding the segment boundary. So it will activate the same mesh set, but change the property from ground to concrete right here. So in this manner, the tunnel boring machine is about to excavate member 9 and 10, and at that time we have our first and second segment member erected. So then we'll deactivate these 2, and we'll deactivate the shield, because once the segment is constructed, the shield is no longer there, it has moved forward. So we'll deactivate the shield members, and as and when we deactivate the shield members, we'll activate the gap loading that we have computed, and obviously the jack force as and when the excavation proceeds further. So this is a cyclic process, as you can see. Then we'll continue to deactivate the members that are being taken out, which are no longer needed, like shield members, and we'll be activating the new segments as and when they are erected. And once we are through with excavating, let's say 8 times or 8 increments or 16 units, then we'll start applying the grout. And for that, we'll be taking out the shield, we'll be activating the shield members again, but applying or changing their material attribute from steel to grout material properties. So and so and so forth. So this in this manner we'll bring in the grouting to fill in the gap. And since jack force is something that is an external force that we are applying as and when the thermal boring machine is propagating, so once it moves from one location to the next location, we deactivate it and then activate it. So J1 outer circle is deactivated when J2 is activated, so that when the meshes are still there, you don't want J1 and J2 both to be simultaneously present and overstress your soil strata. Alright, so I think you are able to catch the idea. So what we'll do is simulate this in a construction sequence using a wizard really quick. So this is our model, and we have applied all the loads as you can see here. So I'll directly move on to the mesh set and model, and go to construction stage and click on construction stage definition wizard. And here you can see all the mesh sets that are available, and in the first stage, that is initial stage, I'll say I need ground. I'll press control button. I need inner circle and outer circle, and I need boundary for ground boundary and load as sulfate, and I click and drag it and just dump it into this first column. So you can see 1 to 20, 1 to 20, and dash indicates that these have been applied. Now after this, I'll apply these assignment rules. So I'll just hit apply assignment rules. Oh sorry, I'll first copy this and click here and just paste. So in this manner you can paste it. So you can see mesh, you can select when you are activating it, is it a mesh, is it a boundary condition, or is it load. So if you don't have this spreadsheet, you can also type in by yourself. So you can select okay, mesh, RA activate, deactivate, postfix, prefix, 1 2 1 2. So it is a way of keeping a count, and after how many stages you have to change it. So start stage and stage increment, and so on and so forth. So once you throw in this set of rules, you can just hit the OK button, and my bad. Let me just paste it. I'll say apply assignment rules and then hit the OK button. So once you apply the assignment rules, you can see the members that are activated and deactivated as you scroll from left to right. So total 17 construction stages have been generated, and then you hit OK button. So once you see under analysis, you'll see 18 construction stages starting with IS, which is the initial stage, and then construction 1 2 3 4 and up to 17. You can also see it here under define construction stage, and the first stage that you are defining, you want to use it for computing the initial stresses, so you don't want any deformations due to sulfate to be included. So I'll just say clear displacement at this point and then say save. Now sometimes they are changing water levels, and I just the way I explained in the last session, you can control the varying water level here. You can include different LFDs here if you are doing a 2D analysis, but since it's a 3D analysis, you don't need it right now. And you can cycle through all the construction sequence like this, and just to verify everything is in shape, I'll click on activated. I'll go to the initial stage here, and I'll monitor this main screen. So I'll put it on this side, and I'll just change the name. I'll just cycle through. So CS1, first stage, second stage, third stage, so on and so forth. So you can see the elements are activated and deactivated, and no other section is being no other clear displacement that we're using. Alright, so in this manner you can quickly see and verify your construction staging, and now we'll apply the analysis control. So I'll go to analysis option, and here I'll go and say analysis case. I'll click add. I'll say it is a TBM construction. So I'll give it some name. I can select from different type of analysis type I want to perform. I'll select construction stage. Sometimes engineers want to consider the seepage pressure or the pore water pressure while construction, which is called semi-coupled, or consolidation analysis, which is fully coupled. So in that case, what you have to do is define stages alternatively. So for one stage seepage, next stage construction, third stage seepage, next stage construction, so on and so forth, like alternating them whenever you want to include your pore water pressure consideration, which is a very generic practice, and I'm sure many engineers are already aware of it. Then we'll use the initial stage for the stress analysis. We can also throw in if you want to use K-naught conditions, and then hit OK and OK here, and then close. Now we are all set to perform the analysis. All you need to do is go to analysis and hit the solve button. While the analysis is being performed, I'll quickly show you what we have in results. So in results, you can extract the results for the lining members, as you can see, or the shield member basically. You can see the displacement and forces in the 2D members, which is actually these segments. Oh, sorry, lining is the 2D member, this is the 3D member, and the deformations in the solid. And more importantly, like I said, different type of engineers need have different ways of looking at the information. So some would appreciate if you just give them the contour plots for your presentation. Some would appreciate it in a tabular format or in a graphical format. So midas GTS has really good tools to interact with Microsoft Excel, and you must be aware of other software that have major limitations doing that. So in GTS you can easily generate these tables very easily and export it into Excel directly, and there you can generate all these kinds of tables. So what I'll do is quickly show you the results part of this model. So this is the same model file, just analyzed, and now we'll quickly go over the results. So while the results are loading, alright, so this is where you see the results. You come to the post-processing stage. You can click on initial stage. You can say displacements in all three directions. So you can see initially we set clear displacement, so this is 0. And let me activate all the mesh sets here. So the mesh sets are activated, and now I can just change the construction stage step from here, and you can see the deformations. And you can see the deformation for the vertical direction only. So as and when the construction proceeds, you can see the deformations and the values. Now you must be curious to find out what's going on inside this analysis, or inside this ground strata. So one way is that you can activate the mesh set and take a look at it. So I just want to look at let's say the inner circles and the outer circles. Show only, so you can see the results only for these members throughout the construction staging. From 0, you can see how the members are removed, and then the segment members are installed. So you can find out the forces in these members directly, like this. And if you would like to get a complete picture, like a section cut, so what I'll do is activate everything. So this is a plot here, and I'll go to the post-processing command, and here I'll say I want to see splice cut. So in this way you can have results at any given section. So let me go to the post data, and let's say for this construction stage I want to see the force at a given place. So you can see You can move this plane anywhere in the cross section along this length and see the results. You can make it sensitive, and once you go to the clipping plane, you can easily arrange this in different layouts. So what I'll do is check on and make this also sensitive, or make some intersections here. So here you can see I can move this plane and see the results at any given area or cross section. And you can also control this movement by giving the length, to what point you would like to have the cut made. And if you have already defined, you can just click here and say I want to see their union. Say apply. So you can see the union, intersection, and let's say I want to make a vertical cut here. So I'll say define, and I'll say along the z-axis like this, and I'll say OK. I'll give it some name. So let's say 3, just to avoid any confusion. Say add. So now I'll use, if I want to see this and say intersection, or let's say union. So you can see it in different planes together. And you can also simulate something called construction stage animation. So let's say I want to simulate the excavation sequence for this particular excavation. I'll say multiple steps, and then I'll say I want to have the excavation from 0th to the full. So I will say OK here, and what the program will do, it will show me the construction sequence for the entire process. So you can see, you can turn off these contour gradients or the lines and see how the construction is being carried out. And you can save this as an AVI file for using later on. So I've saved one file for you. I'll quickly show it how it looks like. This is the file that I just created, and I'll open with let's say Windows Media Player. So you can have these kinds of results obtained, and you can save them as an AVI file. You don't need any external software for this. You can save them in AVI file and then use it in your presentations to your owners and clients. Alright. So now this being done, so I showed you how to generate contour plots, how to generate animations and cuts and clipping planes. Now what I'll do is quickly show you how to generate tables or extract results in a table format. So I'll go to results at the top, go to extract results, and let me just go to the pre-processing stage for now. So I'll switch to post-processing stage. I'll go, and I want the result to be at the top of the crown. So what I'll do is just come to the front view and select all the meshes. So I'll go to mesh, and I'll just select by windowing in such a manner that I just get to select the inner mesh, because I don't want that here, and I'll say right click and hide, so that you can see all the members are removed. Now what I'll do is go to result and result extract, and here I'll say I want the results for the vertical deformation, DZ, and I'll say select all the points here, and I want the result at, let me just zoom in at this location. I want the result at the top of the crown, so I'll just select all the nodes here, so you can see the nodes are selected, and then I'll say table. So the program has generated this kind of table where it has given me the deformation at each and every construction stage at that particular node, and all I need to do is just easily copy this and just paste it here. And if you want to create some sort of tables or let's say graphs, that's very easy. What you need to do is just say, this is something Excel based, not really something to do with GTS. You can just select here, you can go to insert scatter plot, let's say this way, and you can see the contours or the graphs, or I think I gave too much data here. Let me show you with a smaller set. Let's say 3. Insert scatter plot right here, so you can see these kinds of contour plots created. And in the same manner, you can extract information and apply it in to different graphs. So let me just hit the delete button here. So this is all I would like to show you, how to extract all these results from one software to another, and from midas GTS into spreadsheet format, and how to generate different contour plots. So this brings us to the end of the presentation. So let's quickly conclude what we learned today. So major benefits from tunnel boring machine construction are structural stability and safety at face and work area, accelerated construction, safer working environment than drill and blast, and better quality control. And second, what we learned today is major challenges in simulating tunnel boring machine sequence are generating the 3D numerical model itself, assessing phase stability and ground responses, and simulating innovations in machine system. And a good modeling or good modeling tools make accurate 3D model generation possible. An appropriate constituted material model would always give you realistic ground behavior during construction. Static 3D model provides best assessment of phase pressure, and contraction pressure on the shield and segments computed as per the estimated or code-defined loss values can be monitored and refined through 3D simulation. So basically you can compute these values, apply to your model, see the results. Like I said, you can make a assessment of a lower percentage, because then you will get more deformation later on due to the creep and shrinkage. So you can simulate, monitor and refine those values. Then contour plots aid quick verification, whereas graphs help in extracting detailed information for the area of interest. Like I showed you, the contour plots, which can be easily used for reporting, and if you want to see the result of a particular node and see its deformation along the length of the construction, you can use graphs. And the result obtained from correct 3D simulation gives confidence to the geotechnical engineer and lead to optimal design by structural engineers. So once you know what's going to happen, you have accounted for all the variations possible, you will have better control over the construction. And once you have extracted the information which is readily acceptable by your contractor or by your structural engineer, you'll be able to have a better communication with them, and structural engineers would be happy enough to get the results in the desired format. And then since the results are accurate, or the design forces are accurate, their design would be much more optimized. And for all the engineers who have attended the session today, and you can convey this information to your colleagues and other friends, that we do these kinds of sessions periodically for absolutely no charge, and all our users join in, and we provide free online trainings to them for different advancements in geotechnical